So this is 2.2.2, ionization and excitation. So to begin with, we're going to recap what we looked at last lesson, where we said that electrons sit within an energy well inside of their atoms. So we'll say, remember that electrons in atoms are inside energy wells. And we represented these energy wells as a sort of square well with our electron sitting inside it. And this top bit here represents the minimum energy required for the electron to leave that atom, which we call the work function. So if the electron receives that minimum amount of energy, called the work function, then the electron will be liberated and will leave that atom. And normally we're talking about the outer shell electrons rather than the inner shell electrons that liberate. So if enough energy, which is the work function, is received by the electron, the electron is liberated and leaves the atom. And most of the time we're talking about outer shell electrons. Inner shell ones can also be liberated, but it takes a lot more energy for that to happen. And also, when photons are incident on an atom, they're more likely to be incident on the outer shell ones first than they are on the inner shell atoms. Exactly, so they also have a deeper well. So the amount of energy needed to liberate the inner shell electrons is going to be higher than the outer shell ones.
So I'm not sure, this might be wrong, but from GCSE, when the inner shells, when they get the excitation, they move up to other shells. Is that still the case?
Yes, and we're going to look at that next. Yeah. So right now we're just looking at ionization. So if the electron has left the atom, ionization has occurred because now you have one fewer or multiple fewer electrons. So therefore that atom has become more positive because it has more protons now than it did electrons. And so overall its charge has become positive and it's now known as an ion. So we don't call it an atom anymore once it's charged. So after the electron is liberated, there are more protons than electrons. So the atom has become ionized. And we now call it an ion. So Now we've looked at what happens when things are ionized. We need the electrons to leave that atom. It can only leave the atom if you supply it with enough energy. Enough energy, we call it the work function, represented by the symbol phi, measured in units joules or electron volts, or mega electron volts. But in reality, the energy wells are not so simple as just one square energy well. They actually have different levels to them. So in reality, energy wells have levels. So now we draw this as a more complicated well. And we draw our electron here. This bottom part here is called the ground state. And these two places here are different energy levels. We also call these excited states. Now, the electrons can only exist at those different steps. They cannot exist in between those steps. So you can't have an electron that's floating around halfway between two energy levels. The energy levels are discrete. It's either in the ground state, or it's in the first excited state, or it's in the second excited state. It cannot be between those different states. So when electrons gain energy to become excited, they have to have that exact amount of energy to become excited, otherwise they won't get excited. And yes?
So let's say that electron, right?
Mm-hmm.
Has energy to go to the first excited state, but it has actually a little bit more to it. So will it kind of reach as much as it can and then drop back down to the
No,
first state?
no, it won't. In the first place, it won't absorb that energy because it won't be able to. It can't do anything with it, so it can't absorb it.
Oh, so only absorb it if it can reach the extra.
Yeah. So these electrons can gain energy from photons that are incident on the electrons. They can also gain energy from nearby free electrons that are just flying around. And it could take some kinetic energy from those free electrons that are just flying past. So either from photons, which we already looked at in previous lesson, or some other electron is flying around, it's free, it's not bound to an atom, it's just flying past. And as it's flying past, our electron goes mine and takes some energy from it. So let's write this down. So electrons can gain energy to become excited from A, photons which have enough energy, and B, nearby free electrons. And when we're talking about nearby free electrons, we're talking about the kinetic energy of these electrons. So the nearby free electrons will have some of its kinetic energy stolen, and so the free electron will slow down a little bit, or a lot, depending on how much energy was taken from it. So I'll put in brackets here kinetic energy. And we'll just elaborate on this, that electrons in the atom can take some kinetic energy from the free electron. So I'll briefly talk about what happens when electrons become excited. We're not going to go into it in too much detail because that's going to be in a future lesson. So we'll actually go over that in 2.2.3. But when electrons become excited, so say they reach the first excited state or the second excited state or the third excited state if it has one, they can't stay there forever. So they've reached that state, they're like, okay, cool, I'm in this excited state. What do I do now? Can I leave? No, I still haven't got enough energy to leave. Okay, I'm going to jump back down then. So they stay there for a brief moment, then they jump back down to the ground state. If they jump back down to that ground state, they have to release that energy. And they release that energy by emitting a photon. And depending on the steps they took to jump down, they're going to release different photons. Again, I'm not going to go into too much detail because we're going to do that in the next lesson. But if they jump in one go, so for example, from the second excited state straight to the ground state, they will emit a lot of energy. If they jump from the second to the first, they emit a smaller amount of energy. Then from the first down to ground, they emit, again, a smaller amount of energy than if they jumped from the top straight to the bottom. And that's what gives you different colors. That variation in energy emits different colors. And then when you look at materials that emit different colors of light, that's all to do with where their energy levels are. Because different materials, different atoms or elements have different energy levels.
So an electron that jumps from the second straight to the first, that releases a lot more energy.
Yeah.
Where the higher energy photon will just have a high frequency.
It'll have a higher frequency and a higher energy. Because E equals to HF.
Okay.
Yeah?
So when electrons are excited, they're kind of unstable.
We wouldn't use the word unstable. So what do you mean by unstable?
It's like with other unstable particles.
No, unstable means it's going to decay. The electrons are not decaying.
But can you conceptualize it like that?
No, you cannot because they're not decaying. Yeah? The electron still remains an electron.
Yeah.
It's just absorbed some excess energy. It's in some excited state, and it says, right, I'm going to jump down from that excited state and release some of that energy. In some form of decay, and this is in nuclear physics, for example, gamma photons, we said before that all radioactive decay comes from where? The nucleus. So in terms of gamma photons, they still come from the nucleus. And the way they come from the nucleus is that the nucleus itself can become excited. So even the nucleus itself is bound in some energy well, and that can become excited. And if it de-excites, it's got a huge amount of energy that it releases. And that comes out in the form of gamma photons. Once it's de-excited, it can also then go through secondary modes of decay.
So does that happen when something to do with the photons, I'm assuming?
Yeah, the whole nucleus itself.
Including the neutrons and...
Yeah. But you'll see a lot of gamma emitters tend to emit other stuff as well. So they won't be purely gamma. They'll emit gamma and they might emit some beta as well. There might be gamma and they'll also emit some alpha, or they might even emit all three. Yeah? Okay, but that's, again, the nuclear part of that is more to do with your second year and about the emission of light and the different frequencies and energies that we're going to do in 2.2.3. So let's move on. Start a new page. We're going to talk about the fluorescent tube. Now, fluorescent tube was actually very, very important, but it's become less common in your lives in 2022 than it used to be in my life in 2010. So, when I was a child growing up, most of our light bulbs at home were incandescent light bulbs. A glass bulb with a small tungsten filament inside it. When you switched it on, a current ran through that tungsten filament. The filament got hot. When it got hot, it started to glow orange, then yellow, and then white, and that was your light bulb. It was basically just a very hot piece of metal that was glowing and emitting light. The light from it was very nice. However, a single light bulb would be using about 120 watts of power. So they waste a lot of electricity. Very, very inefficient, and they get very hot. Then there was a development of the energy-saving bulbs, which were fluorescent tubes, and they let us have 20, 25 watt bulbs that emitted the same amount of light as 120 watt incandescent bulbs. Nowadays, everyone's switched over to LED bulbs, and now you've got 10, 12 watt bulbs that are emitting the same amount of light as a 120 watt incandescent bulb. So leaps and bounds in efficiency. And they get a lot less hot. So with a LED bulb, for example, you can touch it while it's turned on. With an incandescent bulb, you'll burn your hand if you touched it while it was turned on. There you go, very, very hot. So we're going to talk about the fluorescent tube and how that worked. It actually works very, very cleverly, but a lot less relevant to your lives now. However, the bulbs that, or the lights that we use in this room, you can't see them because it's a cover, but actually inside here, there are fluorescent tubes. You might have seen those tube lights before. Yeah, the long tubes. Those are fluorescent tubes. So first let's construct a circuit. So we have an alternating current supply. That then goes inside our fluorescent tube. So this is our fluorescent tube here. And when it enters a fluorescent tube, it goes through a filament, which is basically just a coil of wire. Then it comes out, goes to a device called a starter. Then goes to the other side, to another filament. Then comes back out and back to the other side of your AC supply. Now, if you've seen these tubes before, can you tell me what material they're made out of? Made out of what material?
Plastic.
They're not plastic. What material is a tube made of? Glass. They're made of glass. Are they transparent? Are they transparent, fluorescent tubes? Can you see through it? Some of you are looking at me weird, like you've never seen a fluorescent tube before.
If it wasn't transparent, you couldn't see the light coming out.
Is that transparent?
Oh, that.
Is that transparent?
Oh, those. That's not what I was talking about. No, that's not.
Is that transparent? Is that transparent? No? Is that transparent? Okay. Even the big tubes are not transparent. Okay, so it's made of glass. Why is it not transparent? Glass is transparent, right?
My
This tube is made of glass. Why is the tube not transparent? No. Because if you were to mix a dye into glass, you would still be able to see through it. It will act as a color filter instead. Actually, there is a coating on that glass, a phosphor coating. So here we'll label that up as phosphor coating. And I'll explain to you why that's important in a minute. Inside the tube, it's filled with mercury gas, or vapor, filled with mercury vapor, plus some inert gas. Now I'll explain how this actually works. So initially, when a current passes through this circuit, we start from the supply, we go around to the filaments, and around to the starter, and around back to the other filament, and then back to the end. When a current flows in a circuit, those filaments will heat up, and the starter will also heat up to an extent. The starter is a special kind of switch where when it begins to heat up to a certain level, it actually switches off. So it's more like a thermal switch. So it switches off. But what happens is when it gets hot, when those filaments get hot, they start to emit electrons. Because the electrons in the filament gain enough energy, they liberate, they escape the filament. When that happens, the starter has also become hot, and the starter is a type of switch that switches off because the contacts move when it gets hot, basically. The contacts move and it switches the starter off. So now that circuit is incomplete from the bottom end where the starter is. But since electrons have started to come off from the filaments, and there is mercury vapor inside the tube, that now behaves as a complete circuit going through the mercury vapor. So now electrons start flying across the filaments through the vapor. So the circuit still continues to work when the starter's off. Yeah? Because the electrons are now flying inside the tube rather than going through the entire circuit of wires. Because that bottom part with the starter, that becomes nullified. It's not a parallel circuit. Technically two pathways, but one pathway is inactive at the beginning when the circuit is cold, and the bottom pathway, which is the starter, is active when the circuit is cold. When the circuit gets hot and electrons are emitted by the filament, then the middle pathway, which is through the tube, becomes active and the starter becomes inactive. So now you've got electrons flying across the filaments where you've got mercury vapor. Those electrons give energy to that mercury vapor. Excitation occurs in the mercury vapor. De-excitation occurs in the mercury vapor. And the mercury vapor emits ultraviolet light. Hold on a minute. Ultraviolet light, well, that's not good for you, right? Causes skin burn, sunburn. Right, so now what happens, you've got a phosphor coating on the edge of the glass. The phosphor coating absorbs the UV. Those electrons jump to a high energy level, and then they jump back down in smaller steps. And when they jump back down in smaller steps, they emit some blue light, some red light, some green light. You put all those lights together, you get what? White light. And now you've turned a tube that emits ultraviolet into a tube that emits visible light. Now there are versions of it that do emit UV. And if you look at the UV tubes, they're transparent. Because they're the same thing, just lacking the phosphor coating.
Just explain one more time about the circuit. The starter turns on, right?
Okay, so the starter has contacts inside it. But these contacts are in such a way that when they get hot, they move. So When a current begins to flow through this circuit, so say if I had a switch somewhere at the top, which is going to be your light switch in your house. Once I turn the circuit on, current flows through the wires to the filament, first filament, out of the filament, down to the starter, back round to the second filament, then back round again and back to zero potential difference. So it completes the circuit. Very, very quickly, the filaments get hot and they start emitting electrons. And also very, very quickly, the starter also gets hot. So the starter turns off. And when the starter turns off and the electrons have already started to be emitted from the filament, that mercury vapor inside the tube completes that circuit. Because now electrons are jumping across the mercury vapor to get to the other side. So the circuit's still complete. If we didn't have the starter in the first place, if that was just empty, then you wouldn't be able to have a current flowing in the first place to heat up those filaments. So say if I erase the starter, pretend the starter didn't exist over there, just blank, no wire as well connecting between them.
So there's no wire connecting the filament?
Yeah, just imagine the starter didn't exist and those two wires were not connected together.
Okay.
Current could not flow in the beginning
That's fine.
because there is no complete path. So in the beginning, current flows like this. In that process, that filament gets hot, that filament gets hot, the starter gets hot. Filaments get hot. What do? They start emitting electrons. Why? Because that heat gives them enough energy for the electrons to escape the material. So electrons start flying out of this. The starter also gets hot. The starter has contacts inside it, so it's a switch. When it gets hot, those contacts stop touching each other, they move. Once they've moved, and these two filaments were emitting electrons, these electrons now start going across the mercury vapor to the other side, and they act like a complete circuit. And this bottom part becomes nullified because it doesn't exist anymore, because the starter is off. Yeah, because the circuit's been disconnected from the bottom. Exactly. So at that point now you've got electrons flowing through the tube, so now those electrons can excite the mercury, and the mercury de-excites, emits UV, then the UV is absorbed by the phosphor coating, and that excites and de-excites in steps, releasing all different colors of light, which gives you white light. Now, let's say instead of a starter, we just had a wire to short circuit this. Okay, well what would happen then? The filaments will still get hot. They might start emitting electrons, right? This filament might start emitting electrons, but they're not going to emit electrons in a straight line to the other filament, to the other side. They're going to emit electrons randomly because they emit electrons in all directions originally. They get hot, they just emit electrons in whichever direction. They don't know which way to. Yeah, nothing is telling it which direction to emit electrons in. So they just get hot and they start throwing electrons in all random directions. And if this was a short circuit here, then think about it. The path of least resistance is through the wire. So the current will just prefer to flow through the wire. The electrons coming off those filaments aren't going to be directed through to the other side. But once it's disconnected, the starter, as those electrons are coming out, if this side is positive and this side is negative, but now an electric field is directing them through, and because now this vapor path becomes the path of least resistance, you get a steady current flowing through the mercury vapor. Otherwise what happens is you have electrons going in random directions. The fluorescent tube, instead of lighting up across the whole tube, you get small little flickers on the edges if you didn't have a starter. Yes? The inert gas is just to fill up the rest of the space and not to react with things. Because if you had gas that was not inert, then it could react with the mercury vapor. And you don't want chemical reactions changing what's inside of it. So a lot of bulbs will use inert gas. So normal incandescent bulbs, they have inert gas so that the tungsten filament, when it gets hot, it doesn't react. Huh? Yeah, noble gas is inert gas. Yeah. All right, let's summarize what's going on here then. Now the main point is not really about understanding how the starter works, rather it's understanding the current and how the current translates into excitation, de-excitation. So I'm going to start the point from the current flowing through the filaments. Yeah? So we write down current flows through filaments. When current flows through filaments, filaments heat up. Causing electrons to liberate. Then the kinetic energy of the liberated electrons transfer to electrons in mercury vapor. Then the electrons inside mercury vapor become excited. So electrons inside mercury atoms become excited. When they de-excite, they emit UV photons. And again, they're emitting UV photons in all directions. You can't control which direction. Because they're in a tube, it doesn't matter which direction the photons go in, all photons will end up on the edge of the tube at some point. Right? So UV photons are absorbed by electrons in phosphor coating or phosphor atoms. These electrons excite, then de-excite. But they de-excite in steps. So these electrons excite, then de-excite in multiple steps. Emitting light of different frequencies. And I'll put in brackets red, green, blue, which give white light. Which is visible light.
So, you don't need to know about how the starter provides why the starter is used.
To an extent, but not in great detail. So the start, if you just know that the starter is used to start the fluorescent tube, that's mostly enough to get you through. So the main point here is about how the excitation, de-excitation works. But obviously if you understand how the starter works as well, then you're in a better position. Okay. I would normally also go through the electron volt at this point, but I think we've already gone over the electron volt multiple times already. So I'm not going to go through what the electron volt is and how we convert from joules to electron volts, because I think at this point everyone knows how to do that. So instead we'll go to a new page and we'll do an example instead. So we'll do a few questions here. We'll do an electron has rest mass of 0.51 mega electron volts. How much is this in joules? B, a photon produces an electron and positron through pair production. What is the minimum energy in MeV? Part C. What is the minimum energy in joules? Put in brackets of the photon. And D, what is the minimum frequency of the photon? And if you want to practice these types of questions by yourself, you can pause the video now, and I will then go through the answers in a few seconds. Right, I'll go through how to solve these questions now. So going up to part A, an electron has a rest mass of 0.51 MeV. How much is this in joules? So I'm going to need you guys to help me with the calculations because I don't have a calculator. So first we need to do some conversions. So we first convert from MeV to EV. So 0.51 mega electron volts is equal to 0.51. We simply replace the mega with what it means in standard form, which is times 10 to the power of 6 electron volts. Then we know that 1 electron volt is equal to 1.9 times 10 to the minus 19. 1.6, sorry. 1.6 times 10 to the power of minus 19 joules. So we replace the EV with times 1.6 times 10 to the minus 19 joules. So that's 0.51 times 10 to the 6 times by 1.6 times 10 to the minus 19 joules. And that is equal to 8.16 times 10 to the minus 14 joules. So that's part A solved. Then for part B, we have a photon that's producing an electron and a positron through pair production. Just going back to what we know from particle physics, how much energy is needed. Well, we know that in MeV, for one electron at 0.51 MeV, we know that a positron has the same rest mass and rest energy as an electron. So we just have to do 2 times 0.51 MeV. So positron and electron have same rest energy. Therefore, E equals to 2 times 0.51 mega electron volts, because that was already given in the question. So the energy is equal to 1.02 mega electron volts. Part C was asking for the minimum energy E of the photon in joules. Now, we can do it the long way, or we can do it the short way. The short way is that in part A, we already found for 0.51 MeV how much that was in joules. So we can just take our answer from part A and multiply it by 2. Or we can take our answer from part B and convert that, which is longer. Yeah, so you could take either way, either take your answer from part B and convert that into joules, or take your answer from A, which was already 0.51 MeV converted into joules, and just multiply answer from A by 2. So I'm going to take the easier way.
So you wrote down the question as what's the minimum frequency?
What?
On the board you wrote what is the minimum frequency?
The minimum frequency, that was question D, I think. Part C is the minimum energy in joules. Part D is the minimum frequency. So we're doing the energy first, then the frequency. So for the energy, we're just going to do 2 times 8.16 times 10 to the minus 14 joules. That's equal to 16 point, what is it? 16.3? 0.2. 16.3 times 10 to the minus 14 joules. And then lastly, we're going to use E equals HF of our answer from part C to find the frequency. So E equals to HF. We're going to rearrange this to find F. So F is equal to E over H. So we put 16.3 times 10 to the minus 14 all over 6.63 times 10 to the minus 34. And that equals to 10 to that, that's 10 to the 20. 2.5 times 10 to the 20, and we put our units hertz. And that's the end of 2.2.2.